Thank you very much for being here this lovely Saturday morning. So today I'm going to talk about searching for dark matter with antimatter. Now, what is dark matter, what is antimatter, and why should we care? So why should we care about dark matter? Well, we care about dark matter because there is a great amount of it. And both today and in the past history of the universe. In our current era, there is about 5 times more dark matter than matter, regular matter that you and I are made of. And in terms of the energy budget of the universe, about 23–24% of the energy budget of the universe is in dark matter. Only less than 5% is made out of light and out of matter that you know. The rest, there is another about 70% that is made out of dark energy, which I'm not going to talk about today. In earlier times, there was even more of dark matter in terms of the energy budget of the universe. So there is a lot of it. We do find evidence for it in many different astrophysical systems, but we do not know what it is. That's why, for instance, I also care about the case where it is black holes, produced very early in the universe. But today I'm going to assume that it is a particle, and I will talk about it in a moment. Now, what is the evidence for dark matter? If we don't know what it is, how do we know it exists? Well, one of the many best examples is from what we call galactic rotation curves. So suppose I start rotating this little ball. I'm exerting a force on it. By how fast this ball is rotating, you can estimate how much force is being acted on it. The faster it goes, the greater the force there is. So the same idea is being implemented on observing the stars in galaxies. So we study where the stars are, and we can study, where the stars are in a distant galaxy based on the light. And based on the light, we assume, let's say, that all stars are similar to our sun. Then we have an estimate. We know how heavy our sun, how massive our sun is. We know how much light it produces, so we can make a conversion between light and mass and matter. So we assume how much light there is. We can, from the profile of the light, we can estimate how much matter there is in stars. We can do the same thing with gas that is between those stars. This is called interstellar gas. And based on that, we can build some profile about the distribution of mass. Based on the distribution of matter, we can estimate from that how much gravity there is, right? Because our sun exerts a gravitational pull on us, so the combination of many, many stars and interstellar gas will create a potential, a gravitational potential from which we can estimate how much force there is. So what happens is, based on that, we can estimate how fast the stars should rotate around the center of the galaxies, of the various galaxies. And it turns out that towards the inner part of the galaxies, they are rotating roughly at the assumed, at the expected speed, but as you're going further and further away, you expect that the speed of the stars and then the gas further out should drop, and instead it keeps increasing. So there seems to be, there is more gravitational pull than expected, and from that we say that there is more matter. And for instance, in the case of our own galaxy, or galaxies like our own galaxy is the Milky Way, there seems to be about 10 times more matter than we would have expected from just observing the stars and the gas. And how far distant are these 10 times more matter? So the closest star to us is about 4 light years. That means it takes 4 years for light to go from the sun, after the sun, from the sun to that closest star. The sun is about 7 light minutes away from us. So we use the light year as a distance, is a measure of distance, and sometimes we use a parsec, which is a little more than 3 light years. So it is within 100,000 parsecs that this 10 times more matter exists than the expected. So it is on a large scale. On a very large scale, do we understand the presence of that dark matter? In fact, you can go a further larger scale up, and you can study, instead of just studying a single galaxy, you can study collections of galaxies, which we call them galaxy clusters. So from there, again, we see by studying the profile and by studying what's the typical velocity of the various galaxies. Now, the galaxies are not rotating all together like the stars are rotating around the center of a galaxy. The galaxies within a cluster of galaxies are just a little randomly moving around, but just from the fact that they are moving with higher speeds than anticipated, again, we come to the conclusion that there is certainly more matter than the conventional matter that we are made of. And it's about 5 times more matter, and that's on a distant scale of megaparsec. Now, megaparsec is million parsecs. Remember in your hard drive, megabyte, gigabyte, terabyte. So mega means a million, giga means a billion, tera means a trillion. So I'm going to use this giga and tera at some point. You can go even a further larger scale up, and much like there are galaxy clusters, or collections of galaxies, occasionally those galaxy clusters collide. And that's a famous example is what we call the bullet cluster, which comes from this, refers to this cluster. So this is the case where 2 big collections of galaxies collided, in reality passed through each other. So now, galaxy clusters are made out of galaxies, which galaxies are made out of stars. There is also the gas that is between the stars and between the galaxies. Now, whenever the collision happens, stars rarely really hit each other. They are pretty tiny, so it's an extremely rare phenomenon to happen. What will happen, though, so the stars are going to pass through each other, but from these 2 collections. But what will happen is the gas is not going to pass through without any deceleration, because there is some pressure, and because there is some pressure, the gas will decelerate, and in fact will create this bow shock. It's the similar kind of thing that your car produces when you're driving very fast on the highway, and you are pushing the surrounding air aside. Now, from that, we understand that from the fact that we observe the gas, and we observe the gas through X-rays, we understand that the collision has happened, that the 2 clusters have passed through. We can observe the various galaxies from optical observations, or observations in light that we can observe, we can see, and you can see right now. And we understand that they are predominantly sitting here and here, but at the same time, from what we call gravitational lensing, we can understand that there is where the gravity is and how much of that is. And it's clear that there is a lot of it, much more than you would expect, than there is from regular galaxies and regular stars. And the fact, so it is much more, and it's also is ahead of where most of the gas is. So that suggests that this matter, this dark matter, there is a lot of it again, and it's present, and it doesn't really interact. It moves as if nothing really happened. It didn't understand much of the collision beyond the gravitational interaction, of course. In fact, we have many other observations from the cosmic microwave background data that you may have heard in these lectures, from observations of supernova explosion. Supernova happen when very massive stars die. We have understanding and indications for dark matter from the distribution of galaxies. So this is our location in the universe. This is, every little dot here is a galaxy. You can see that these galaxies are not distributed randomly. They are distributed on a very filamentary manner, right? There are lots of gaps here and then a lot of galaxies sitting all together. And wherever there is red, it's, there is quite a lot of it. So you can see that there are definitely, the distribution of galaxies is very not isotropic and not homogeneous. Well, it is isotropic and homogeneous on an even larger scale. But on that scale, it's pretty filamentary. And that is a prediction from dark matter. Moreover, there is another prediction of that dark matter, from dark matter and from what we call cold dark matter, which I'm not going to go further on that, about how the structure of the universe, how the growth of structure in the universe happened. So what has happened is, in the history of the universe, first the stars were created. Then those stars started creating collections of stars. Then those first collections of stars became small galaxies. Then small galaxies started merging with each other, producing bigger galaxies. And from there, from these bigger galaxies, we started having even bigger galaxies by absorbing and eating other smaller galaxies around them. And then these galaxies started creating groups of galaxies. In our group of galaxies, Andromeda is the closest and the biggest member. This is the local group. And then those groups started creating clusters of galaxies, and then those clusters of galaxies created superclusters of galaxies. So that was the history, from small scales to larger, larger, and larger. And that was another prediction that came from what we call cold dark matter. There is also suggestion for the presence of dark matter from the fact that we understand pretty well now how the various nucleus were produced in the Big Bang, and also in what we call lensing, gravitational lensing. The gravitational lensing was actually what we needed here to understand where the gravity is. Now, okay, I told you about suggestion, so what do we understand about dark matter? So I told you let's say it is a particle. There is a good indication, a good theoretical motivation has been there for a good theoretical motivation for why dark matter could be a particle. If dark matter is a particle, and I will call that with the Greek letter chi, then that particle, it turns out that for a specific mass of that particle, or a mass range of that particle, you could have had produced that in a specific type of interactions with known particles. Here F refers to fermions in reality, but what I mean to say predominantly here is something that is a known particle that we have detected in a lab on Earth. So if there is some type of there is a case where a dark matter particle of a mass range of 100 times roughly the mass of the proton could be produced early on in the history of the universe and at a proper amount. Given that I told you that there is about 5 times more matter in dark matter than in regular matter, we understand how much amount of it exists. So we built theoretical models to explain at least the amount of it. And one of those is what we call weakly interacting massive particle, or just WIMP, WIMP dark matter. So there is matter dark matter, there is WIMP dark matter, there is fuzzy dark matter, there is primordial black holes dark matter, there is a lot of different versions of dark matter, and we try to be fancy about our naming. So I'm going to talk about WIMPs today. So this WIMP dark matter is something that, if it is true, it's passing through your body at every given moment. So for instance, if you take a quart of milk in your refrigerator, it has something like 100 trillions, 2 times the word trillion, protons in it. Well, it also has actually 1 dark matter particle in it, roughly. Now, it doesn't have the same dark matter particle in it there, because those dark matter particles are moving very fast through that quarter of milk and through your bodies. They move at a velocity that is something like a little more than 200 kilometers per second. So that's pretty high, right? That's more than, it's about 120 miles per second, not per hour. So we have an idea about it. Okay, what's next? Well, we are trying to understand something about new physics here, right? So we are trying to search for new physics, and we are trying to understand something about the interaction of these dark matter particles with known physics. So we say, okay, let's say this is something like 100 times the mass of the proton, or just 100 GeV. Remember G for giga. So it's 100 GeV. What's F here? It's some known particle, what F is actually, and what's the blob here? So we try to understand that. Now, by having theoretical models, that's good, because you can actually build experiments around them. And that's what we do. So, for instance, we built deep experiments, we built experiments deep underground, and we searched for the very rare occasion where that it particle, the dark matter particle, scatters with regular matter. So occasionally, very, 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 very rarely, and by very, very, very rarely, I'm talking about experiments that are a portion of this room filled out with various target material, and try to search for one scattering, one interaction of dark matter with regular matter in a year. So you have this very big volume, and you're trying to search something extremely, extremely rare. So this is called direct dark matter detection. So you are trying to just see if it scatters. This is a scattering reaction in the end, interaction in the end, a scattering event in the end. So you're trying to search if it happens like this. And then in this sense, the time is going either this way or that way, but we are talking about something that there is an interaction. Now, there is also the case where we are trying to produce dark matter colliders. So I'm seeing that diagram in this way in this case, where what we are doing is we are accelerating regular particles, like protons or protons and antiprotons, and collide them and hope once they collide, they have enough of energy to produce that dark matter particle. This is a common thing that we've been doing in collider physics for decades. We are colliding particles and hope they have enough energy to produce new particles that exist there but are not, on an everyday level in our life. And now the third way is we are just saying that occasionally these dark matter particles may find each other, collide per se, annihilate in reality, and produce regular known particles. And this is things like leptons, quarks, and Gates bosons. Gates bosons are force carriers, are responsible for various forces in nature. Leptons are electrons, for instance, are leptons. And quarks are the constituent particles that compose protons and neutrons that we are made of. Now, you hope that you produce those known particles that we know that definitely exist because we've produced them in the lab, and then they go through various processes that we understand. This is known physics from here on, and produce stable particles that we have detected and we've known. And those are the protons, and their antimatter particles, the antiprotons. There are neutrinos, there are electrons, and the antimatter particles, positrons, and also various photons like gamma, very high energy gamma rays, or radio waves, or optical, or you name it. And it is actually those particles, and the search for those particles that I will focus on from here on. This is called indirect dark matter detection. It's called indirect because you're trying to see it indirectly. You have no control whatsoever. In the case of this, And this, you have a lab. This is a laboratory, this is a laboratory, so you have some level of control. Here, you don't really have any control of what's the physics, what's happening here. You only have various detectors that you're using the data from, and you're trying to search in the data if there is something interesting. And in fact, these are the basic questions that we're trying to understand in my field, which is how can we use the data? How can we maximize the use of those data? Is there any signal, anything interesting lurking within those data? What control do we have about on the other astrophysics, theoretical astrophysics questions? How well do we understand sources of possible, say, cosmic ray antimatters? So what are the theoretical uncertainties into what is a prediction for what a signal might be? And also, what if dark matter is not living in that specific energy range and would never produce a signal in the data that you're looking for? So you need to ask the question, could that data that I'm going to analyze, could they ever have a signal for dark matter or not? Is there anything interesting? And how well do we understand all the other stuff that are contributing into the data? So this is where antimatter comes in a very dominant way. Now, this is a diagram of our galaxy. This is what our galaxy would look like to a distant observer. And we know that there are cosmic rays. Cosmic rays are charged particles that have a lot of energy. Now, we know that cosmic rays are produced whenever big stars die and there is a supernova explosion, because then these stars accelerate the material around them. The supernova itself, there is a big shock. It accelerates the material around it, and it produces the cosmic rays. And we have some understanding about these cosmic rays. These cosmic rays propagate within the galaxy. I'm not going to go further into what are the processes of propagation, but the dominant one is something like random walk in 3 dimensions. So random walk is, imagine you are, imagine the case where you're an observer and you have someone who's really, really drunk. That really, really drunk person is moving in a random way in 2 dimensions, like on the street. Well, cosmic rays do that in 3 dimensions. So they do walk randomly from the various sources, and occasionally they reach the sun. But now we want these new dark matter particles that we call chi. They may occasionally produce, also as they annihilate, they will produce antimatter. And the difference between the dark matter and the regular matter is the regular matter doesn't like to produce antimatter. It's very, very rare. The dark matter is a very different type of matter. It doesn't have any reason to preferentially, when it annihilates, to go directly for just matter. For it, matter and antimatter are basically the same. So whenever it annihilates, it's likely that it will produce equal amount of matter and antimatter. So this is why antimatter is interesting in the story of dark matter. Because dark matter would produce equal amounts of matter and antimatter, while regular matter cannot very easily produce antimatter. In fact, this type of probes connects with other data that we have to use in parallel. So this type of analysis and work relies not just on using cosmic rays, it relies on using high energy photons, which we call gamma rays. This is our galaxy. This is our own galaxy. This is the center of our galaxy. This is how we observe the sky in gamma rays. This is how we observe the sky in radio waves and in microwaves. So we have observations of cosmic rays. We have other observations as well. And together, all those things together give us an understanding of what are the processes that are taking place in the galaxy that we live in. Now, experiment-wise, I told you about data. I was talking about we use some data. So what are those data? Those data come from various experiments, including data that we'll talk about today, which comes from the alpha magnetic spectrometer. This is a big detector in space on the International Space Station. This is the International Space Station. This is the AMS. It was launched and it was placed on the International Space Station in May of 2011. It's a really big instrument in the sense that it's about almost like 3 meters tall and about a little more than a meter wide on both the dimensions. It's something that could fit in the second to last space shuttle launch mission. And it detects, the AMS detects cosmic rays. It's basically the biggest detector, particle physics detector we could fit into the space shuttle and get it up there. And it has a magnet, it has tracker, it has various different materials. The important thing is from that you can understand the charge of particles, whether it's a positive charge or a negative charge. You can understand how much energy those particles have, and you can also understand whether it's a proton or an an electron, or the antimatter particle of a proton, which is the antiproton, and the antimatter particle of an electron, which is called the positron, together with a lot of cosmic ray nuclei. So it does a great job in making measurements of cosmic rays and helping us understand the cosmic ray physics of our galaxy. Now, one of those measurements, probably the most well-known, is what we call the positron fraction. The positron fraction is just the number of positrons, the antimatter particles of electrons, over the total electron and positron number of electrons and positrons. And it's a flux, so you have a lot of these particles passing through your detector and getting detected. And then you have that ratio versus energy. And energy here is in GeV. Again, the mass of a proton is a little less than a GeV. So it goes all the way from 1 GeV to 1 TeV, 1,000 GeVs. And it's something that it was at low energies. As you start from lower energies and you start going to higher energies, initially you see it going down, then it kind of flattens, and it flattens it starts with being 0.1, meaning that for every 1 positron there are about 10 electrons. Then it drops to about 5%, so it means that for every 1 positron there are about 20 electrons, and then it starts going up again to something that's close to 0.2, so it's something like for every 1 positron there are about 5 electrons. The fact that it went up was very, very surprising to us. Now, the other thing was that it was pretty smooth, which was very interesting, and that we kind of observed that. We tried to ask ourselves whether we observed that those positrons coming from any particular direction, and it seems that they are coming from all directions pretty much in the same, with the same flux. So there is no preference of those positrons coming from one specific, towards, say, one specific, as if they were coming from one specific distant star, or not so distant star. So why was it interesting? Well, it was interesting, the fact that it went up, because we have an understanding, again, where cosmic rays are produced. Cosmic rays are produced whenever a supernova takes place, whenever a big star explodes. This is Tycho's supernova, and this is this image of that in X-rays. So what happens is there is this explosion, there is this huge shock wave moving outwards, and what happens is particles get trapped in this very, very fuzzy region, and they get accelerated, and then they get injected back into what we call the interstellar medium, like the region between stars, but now they have this very high energy. Very few of them, but with very high energy. So that's where cosmic rays are produced, but then this is where actually cosmic ray protons are produced, regular matter, And cosmic ray electrons are produced, regular matter. Positrons are not produced there. Positrons are produced later on as cosmic ray protons are propagating within the galaxy, are doing this random walk, this drunken walk in 3 dimensions, and very, very occasionally they interact, they collide with other sitting protons, very, very, very slow moving protons, and produce positrons. But then, based on that, we had some expectations. We expected that that ratio, and this is with earlier data, we expected that that ratio should drop with energy. And the idea was it should drop with energy. It didn't, and at low energies, it does drop with energy, right? At low energies, it does drop with energy. So our expectation was it would keep going pretty much. It would keep dropping as energy went up. So it didn't. So the question is, there is something interesting here. And that's where people like me started asking questions. Is it possible dark matter? Is it something about the supernova, the supernova physics that I told you that is not accurate enough in the story? Or is there other sources of positrons? And one of the sources of positrons is called pulsars, which are neutron stars. These are very, very dense remnants of dead stars from very massive, or originally very massive stars. So there is definitely some additional source of positrons, of antimatter particles. So definitely there is some new physics happening there. Maybe something fundamentally new like dark matter. So I'm going to assume what would we learn from, I'm going to show you what would we learn from that case. Again, the basic diagram we're trying to find is something, say something about this, the mass of this particle, chi, say something about the blob, and say something about this particle F. The something about this particle chi is that if I observe hundreds of GeVs of positrons, which are produced here, this must come from a particle that has at least even more of mass. So that we say that the particle of the dark matter particle should be something like 1,000 times a GeV if you observe hundreds of GeV of positrons. The other thing you're trying to understand is the amplitude. So this is your theoretical expectation, right? This is your theoretical expectation. This is where your data sits. So you need to produce that many more positrons to go from here to here. That will tell you something about how often that interaction happens. And this is called, what we call in physics cross-section. So cross-section has to do with how big one particle looks to another particle. Imagine you have 2 balls. There is a big difference between those 2 balls, and you're trying to collide those 2 balls. It's a difference between those 2 balls being ping pong balls versus being bowling balls. Bowling balls have bigger cross-section. Similar in this case, in particle physics, we care about the cross-section that tells us how likely they are to find each other and annihilate. And it turns out that just to explain that already was surprising for us. It was beyond what we expected would be happening in the very early stages of the history of the universe, where that dark matter was being produced. Third is that it has to produce a lot of electrons and positrons, preferentially electrons and positrons. So by just having one observation, we were able to say something about all the important constituents of this diagram, something about the mass of this object, something about the cross-section, and something about what particle it produces. In reality, we go further deep, and we can be very model dependent and build models and then try to test those models compared to other observations, which we've been doing the last 10 years or so. And it turns out that nowadays there is only a small number of models that have survived those multiple different tests. So this is what we've learned from using the antimatter particles of the electron, which is positrons. What about the antimatter particles of the proton, which is called antiprotons? So now, how our antiprotons are produced? This is a cosmic ray proton originally. It moves randomly around the galaxy. Occasionally, it will hit a target proton in the interstellar medium, in the gas that is between the stars, and there is a very strong collision. And whenever that collision happens, sometimes it does produce protons, but it also produces an antiproton. Say in this case, there would be 3 protons and 1 antiproton. You have 2 protons originally, and then you have the 2 protons and then from that collision, you produce an extra proton and an antiproton. So that's relatively rare because it actually requires a lot of energy from that original proton. So it's not something easy to produce. In fact, we have an idea how often that happens. That type of interaction happens only for 1 in 10,000 cosmic ray protons. That means for every 10,000 protons of high energy, we only observe 1 antiproton at that same energy. Remember, if with positrons, the ratio of positrons to electrons was more like 1 to 10 or so, and varied between 1 to 5 and 1 to 20. But here we are talking about something that is 1 to 10,000. So 1 antiproton for 10,000 regular protons, all of those of high energy. So just see the green band. The green band shows that in fact, in reality, it's something between 1.8 times 10 to the minus 4. So 1.8 antiprotons in 10,000 protons to 2. And then it goes back down a little bit. Now, the question is there room for that to happen? Is there room for a dark matter to produce some kind of interaction? And now, after all the blob, the physics here, you will produce protons and antiprotons. That means, in order to do that now, you need to have an understanding that is very, very high level, right? I'm talking about some interactions that already are very rare, right? And I'm asking if within those very rare interactions, there could be some even more rare interactions taking place in the galaxy. So that has been something that actually people started wondering about that. So people started asking questions in terms of, well, is there any room for dark matter? And that was something that started a few years ago, and it created a large debate. In reality, I've worked with all of those people one way or another, and I can tell you that all of them are very smart people, and they know their job, but at the same time, they cannot agree. Some say no, some say yes, and some say it's too difficult to say. And some say, well, maybe yes. What's maybe yes? In science, we cannot live with maybes for too long, right? So this is, again, the cosmic ray, the antiproton to proton ratio. It is, again, this 10 to the minus 4. These are the data. The gray band is the uncertainty of the theoretical uncertainty. The purple are the data points. And these people said maybe yes, meaning here there is some indication for an additional component. And the red line would be the additional component. And in terms of what would fit it, again, trying to understand in this question, trying to say something about the matter, the mass of the dark matter particle, and the interaction, and what's the first product. These people said something that this dark matter particle has to be something like 50 or 100 times the mass of the proton, and has to have a cross-section that is really, really tiny by comparison to anything you know in your life. But in terms of the dust line, it kind of fits where the dust line is. And the dust line is not any random line in physics, in dark matter physics. They are exactly the type of cross-section, the type of of how often those dark matter particles would meet each other today that would be necessary for them to have met at the very beginning of the universe so that they were produced. So the same cross-section, the same magnitude of that blob that happens today in interaction happened at the very early on in the history of the universe, where these dark matter particles were produced. That means that we have a good motivation. That means that the same type of interactions that are happening today to explain these antiprotons happened at the very beginning of the universe to explain how much of dark matter is in the universe. That simplifies the idea, the whole theoretical ideas. You don't need to put too many new physics, you don't need to say way too many things about these blobs. Well, so why is there a lot of debate, though? Well, there is a lot of debate exactly because we have what we call in physics uncertainties. So part of our jobs as physicists is actually to quantify and understand those uncertainties. It's not just one data point. The answer is never exactly one number. It's one number with some uncertainty. The distance from here to your home is not exactly 1.10000 miles. It's 1.1 mile or 1.10 mile, but then there is some uncertainty of maybe a centimeter, right? I mean, where do you define, first of all, the distance to your house? Do you define it to your door, or do you define it to the beginning of your property, or something like that? Even if you define it very well, you still have some uncertainty. So similarly, in physics, we care a lot about the uncertainties. And the uncertainties in this case relate to exactly what happens, what we call the cross-section, exactly what happens here, relate to then, assuming it happened, you produced it, and I mean, what happens and how often do you produce and how many of those antiprotons do you produce? Occasionally you can produce even more. If that particle has extra energy, then you could produce multiple antiprotons. So what's the cross-section? Something about the collision, i.e. something about the collision. How well do we understand the collision? How well do we understand this random walk of all cosmic rays within the galaxy? That drunken path, how truly random is it? And also, even a drunken person will at some point find a wall and won't be able to go through the wall, so will have to move around the wall. So there are things that, even to a drunken person, stop them from doing a truly random path, similarly with cosmic rays. So how well do we understand the propagation of cosmic rays in the galaxy? And third, how well do we understand what we call solar modulation? Solar modulation has to do with the fact that we live very close to the sun, and if you are a cosmic ray physicist, the sun is a very big deal. It affects things. So I'm going to only focus on how we do the third thing, because the answer to the first is we have a lot of experiments. The answer to the second, we have a lot of data. I will show you what we do with the third part. The third part is how do we do with the sun? Well, the good thing about the sun is we do have also a lot of solar data. This is the number of sunspots since already the 1800s. And you see that the number of sunspots on the sun has this very evident periodicity of about 11 years. So it goes up, goes down, up and down, and has been doing that. We've actually have observations ever since the 1600s. Early and good understanding already from some time in the 1700s. So we have been observing the sun for quite some time. And in fact, not only have we been observing the sun for quite some time, but we understand now that there are very clear correlations between this number of sunspots and what we call the magnetic field of the sun, which we have been observing since the 1980s. So ever since the 1980s, we've put satellites that observe the magnetic field from the sun, from what is actually called the solar wind, which comes out from the sun. And we have seen that there is a time correlation. Whenever there is a lot of sunspots, the magnetic field is also large. We now also understand that the magnetic field of the sun, while it has this 11-year periodicity, in reality it has a 22-year periodicity in the magnetic field. So the sun has a magnetic field, much like the Earth, and it has a north pole and a south pole. Now the magnetic field of the Earth, the north magnetic pole and the south magnetic pole are not fixed. They change slowly, but very, very slowly, and it's something that happens very, very slowly. But with the case of the sun, every 11 years, the polarity of the sun's magnetic field changes. So every 11 years, roughly, the north magnetic pole of the sun moves where the south was, and the south where the north was. And that creates, and that's something that we have observed by now. Now, on top of that, the sun, because it has a pretty strong magnetic field, it produces what we call a termination shock and a heliopause. Now, the termination shock is a place where the sound speed, much in the same way that we have sound speed on Earth, on the atmosphere, there is a sound speed on the interstellar medium or interplanetary medium in this case. So the sound speed the termination shock is where the sound speed of the solar wind becomes what we call subsonic. If you open the faucet at your home, open your faucet, you will do an experiment. You can do an experiment, and you'll see that the water is moving away from where it lands, right? And then there is a thin layer of water, and then after that thin layer of water, there's a very thick foamy layer of water, right? You open the faucet, you see the water falling on the surface, there is a tiny thin layer, and then there is a thick layer. The transition from the thin layer to the thick layer is the termination shock as well. So there is something equivalent that happens in 3 dimensions around the planet. And it extends out to 100 times roughly 100 times the distance that there is between us, Earth, and the sun. 100 astronomical distances. So we understand that it's there. We understand its structure. It's a very not spherically symmetric structure. It's something it's more like a big spiral. We understand that wherever the transition from the North Pole to the South Pole, it creates a big, thick layer, like a thick blanket, where the magnetic field is very peculiar and very turbulent, very kind of random per se. We understand from that how cosmic rays propagate. That's where the impact of the sun comes. The sun, effectively, the magnetic field of the sun creates something like a magnetic focus. It creates something like a magnetic trap and a magnetic bounce. It traps particles particles of different charge propagate differently follow very different paths within that volume. So what happens is particles at the time where the polarity is where the North Pole is. So when the North Pole of the sun is positive, is on the plus direction, we have a positive polarity, and then what happens is that negatively charged particles, like antiprotons, will come to the Earth from outside by following by going through that blanket region, while, for instance, the protons will come through the poles, come through the magnetic poles. So what it means is that a proton would be moving in this case, a proton would come through the poles, while an antiproton would have to come through this region. And we have to model for that. And we do model for that because we have cosmic ray data. And we actually can go further back in time, and we can use data ever since the 90s. And this is how our approach is in understanding the uncertainties. The answer to the problem, there is too much modeling. There are too many parameters to think about. And there is too many uncertainties is yes, yes, and yes. But also, there is a lot of data. Data and observations from multiple experiments. And I've been mentioning, by now must have mentioned experimental data from about a dozen of different experiments. And I didn't even tell you about all the experimental data that we use from our labs, but which we rely on. Anyway, we have data, we can understand the parameters, we can fit the parameters, and we can quantify the uncertainty. And this is the uncertainty. So this is the data from the AMS, the alpha magnetic spectrometer. This is the antiprotons to protons, antimatter protons to protons, as it goes up with energy, and the bands explain the different astrophysical, the various uncertainties. It relates to the collision, the cross-section, it relates to the conditions of where those protons are produced and how they propagate within the galaxy, and it connects to the impact of the sun. So the remaining uncertainties are these bands. You can see that, well, hopefully, you could see that there is some peculiar thing happening here. Here is where the data are above the band, the uncertainties. In reality, there is also something here. All the fast for dark matter is actually associated with that. So the question is, even these uncertainties, while there is this band looks very thick, this band is never something that it means that every single data point could be, one data point could be here, the next data point could be on the very top of it. It's not that unrelated. These data are related to each other, even on the theoretical perspective. So the reason why there is something interesting here is because indeed the data go, if you look carefully enough, it seems to be low, and then it moves a little high up, and then it flattens out. So there is a little bump here. And in fact, that bump is not that insignificant. Again, in terms of a cross-section and mass, this is the mass of the particle. This would be, again, for my blob of the dark matter particle, this would be a particle that has something like 50 to 100 times the mass of the proton, and has a cross-section that is something close to that dust line. It's the same dust line as before. But it's something that's pretty dominant. So there's certainly some excess here. That same excess, we've detected it from various different groups in gamma rays, in very, very high energy photons. And there's also something at the very high energy that may be related to actually to supernova physics. And in terms of the antiproton to proton ratio, this is the antiproton to proton ratio, and the green dust line is the additional component. This is what I'm talking about. And we are talking about something that is at the level of a 10%. Only 10% of those antiprotons that we observe could be coming from dark matter. But at the same time, there seems to be a 10% excess. This is the level I'm talking about. So I'm saying that for every cosmic ray proton, for every cosmic ray, for every 10,000 cosmic ray, for every 100,000 cosmic ray protons, there are 10 antiprotons, and of those 10 antiprotons, 1 may be coming from dark matter. 1 is anomalous. So there is something interesting in that. So there is some excess. What else should we search for? We should search for heavier antinuclei. I'm going to go even heavier now, even more exotic. This collision happens, the same collision. I told you if it's very energetic, it produces more of antimatter. Now I'm going to imagine that it's really high energy. It produces an antiproton and an antineutron. Antineutron is the antiparticle of a neutron. If those antiproton and antineutron are in the situation where they're both very, very close to each other and they're coming out of the collision with momenta that are almost parallel to each other, then they can merge or coalesce and produce what we call a cosmic ray anti-deuteron. Deuteron is a heavy hydrogen. It's a proton. It's a proton and a neutron. Anti-deuteron is an antiproton and an antineutron. And we call it anti-deuteron, and we can search for that. And we can also search for anti-helium. Anti-helium meaning it's like helium but with antimatter particles. And we can ask ourselves, this is what the sensitivity is. This is what the theoretical expectation is. So given the sensitivity of our experiments, we should never detect any such events. We are a factor of 30, or pi cubed, as we say sometimes, away, or we are a factor of 10 to the 4 away. So we should never observe any anti-helium 3 or anti-helium 4. This is anti-helium 4, this is the regular helium, and this is the regular anti-nucleus of the regular helium, and this is helium 3. There is a lot of helium 3 as well, but not as much and this is anti-helium-3. For antimatter, actually the ratio is very reversed. You have much more anti-helium-3. You would expect to have much more anti-helium-3 than anti-helium-4 for the simple reason that to produce higher and higher antinuclei, more massive antinuclei, you need more and more of the original energy of the proton. That's why it's very rare, and that's why we search for it. And much in the same way, we can study all the uncertainties for these antiparticles. We can study all these uncertainties for these antiparticles. And the reason why we want to study is actually because we have observed now anti-helium, both 3 and 4. We have observed 6 anti-helium events and 6 anti-helium-3 events and 2 anti-helium-4 events. And for that reason, we need to understand the uncertainties. These are the uncertainties of antideutron. These are the uncertainties of the various antiparticles. So this is the flux of the axial flux of antiprotons. 10 to the minus 2 refers to something like, it doesn't really matter. Think of this as how many antiprotons there are, the green band. The blue band is how many antideutrons there are, 100,000 times less. That's how fewer should be in the galaxy. This is how many anti-helium events there should be. Another 10 to 100,000 times less such particles. And this is anti-helium-4. So this is what you would expect from no interesting regular physics. This is what you could expect from dark matter. Dark matter would give you far, far, far more. Here, this is orders of magnitude. This is times 10. Every time is every little slide here, every little line here is a factor of 10 more flux. So you could observe many more. And in fact, the answer is how much more, given the flux, given the sensitivity, the answer is you could observe if the antiprotons are true, if this 1 in 10 antiprotons is from dark matter, then you should expect anti-helium and anti-deuterium events, given certain assumptions for the physics of our galaxy, which are valid and allowed, still allowed. And this is my conclusions. So the point is, we definitely, by searching for dark matter in antimatter data, we have been able to constrain models. We are able to constrain models. And by specifically looking on antiproton particles, we have been able to understand now that there are anomalies, much in the same way that there were anomalies with positrons, and they were well understood, and that meant something about dark matter, the allowed dark matter conditions and properties. We can do the same now with antiprotons. We call that an additional component. And accounting for all the uncertainties, we're pretty certain that this additional component is there. It's not something anymore that has to do with the instrument or something that it needs nothing to do with the instrument. It's theory. There is something in the theory there. And among the possibilities is a dark matter signal. And in the case that it is a dark matter signal, then that dark matter that produces antiprotons can produce antiprotons, can produce antideutrons, can produce anti-helium events that we observe. Not antideutrons, but we have observed anti-helium already. So thank you.